Welcome to the deep dive. So today we're taking a bit of a shortcut. We're getting straight to the kind of strategic knowledge that really defines modern network expertise.
And we're doing that by looking at a really interesting source. It's not some, dense industry report.
Not at all. We've got our hands on the preparation documents for the D-NWG-DS-00 exam.
Exactly. A high-stakes test. And what that does is it gives us a map. It shows us what the industry considers absolutely essential knowledge for an expert in data center networking.
It's the ultimate cheat sheet, really. So before we dive into the tech, you found a fascinating breakdown of the topics in these materials.
I did. And it's really revealing. You'd think it's all about scripting and, plugging things in.
Right, the hands-on stuff.
But look at this. Concepts are just 11%. Deployment support is 9%. Even documentation, which is always important, is only 16%.
So where's the rest of it?
Here's the single biggest nugget we can pull from this. Planning. Planning takes up a massive 51% of the focus.
51%.
More than half the job. It's not just about knowing how to do something. It's about the strategic why. Why this architecture? Why these resilience checks? The design and the readiness, that's the whole game.
That completely reframes the conversation, doesn't it? It means the wisdom is in the blueprint, not just the execution.
Precisely.
So let's start right there with that crucial 51%. Let's get into the blueprint. Modern data center architecture.
And if you're talking modern architecture, you were talking about one thing.
Leaf spine. It's the undisputed king today.
It absolutely is. The whole design is built to maximize what we call east-west traffic.
So server-to-server communication inside the data center.
Right. It creates these very predictable high-bandwidth paths. But, and this is a big but, to really unlock its power, you have to be using layer 3 routing throughout the fabric.
Okay, so that brings us right to our first big question. In that layer 3 leaf spine world, where does a server's default gateway actually live?
And the key answer, the one experts have to know, is that the default gateway for those servers resides directly on the leaf switches.
On the leaf switches. So not on some centralized core router like in older design.
No, and that's the critical distinction. It's all about load distribution and using your bandwidth effectively.
Okay, break that down for us. Why is putting it on the leaf so much better?
So when the leaf switch acts as the gateway, it can immediately start routing traffic up towards the spine layer.
Right away.
And because every leaf is connected to multiple spine switches, and we're using layer 3 routing, this enables something called eCMP.
eCMP, equal cost multipathing.
Got it. It lets the fabric use all the available paths at the same time.
So you're not just letting links sit idle for failover, you're actively using everything you paid for.
Exactly. It spreads the traffic out. It eliminates the bottlenecks that just plague those older 3-tier designs.
Okay, so the leaf is handling all that internal traffic beautifully. But eventually, the data center has to talk to the outside world, right? The WAN, the internet.
It does. And you need a very specific strategic exit point for that.
Which brings us to the role of the border leaf.
That's its whole job. Think of the border leaf as the designated ambassador between your internal data center fabric and everything else.
It's more than just a doorway, though, isn't it? If we're sticking to that 51% planning rule, this has to be a pretty intelligent doorway.
Oh, absolutely. Its main function is connecting to those external routers, yes. But strategically, it's where you handle routing redistribution.
So teaching the outside world about your internal networks and vice versa.
Precisely. And just as important, it's your policy enforcement point. This is where you put your access lists, your traffic filters. It's the gatekeeper that secures the boundary.
That makes a lot of sense. So we have the blueprint. Now we need to actually build it.
Right. Time to connect the concepts to the physical world. Let's talk about the backbone, because a brilliant architecture doesn't mean a thing if the cables can't keep up.
Agreed. And speed is everything. We're pushing to 400 gigabit Ethernet now. So what's the hardware? What transceiver form factor is dominating those 400G deployments?
The answer that every expert needs to know right now is QSFP-DD.
QSFP-DD. The DD is for double density.
And that's the magic right there. For 100 gig, we had the QSFP-28. The DD version, it essentially doubles the number of electrical lanes inside the same physical size.
So you go from 4 lanes to 8.
And that's what gets you to 400G. It's an amazing bit of engineering.
But packing all that into a tiny module, that must have huge implications for that 51% planning phase. I'm thinking about power and especially cooling.
You are thinking exactly like a network architect. It absolutely drives thermal planning.
It's not just about speed then.
No, you're maximizing bandwidth per square inch, which means you're also maximizing heat per square inch. Those high-density ports mean the chips, the ASICs, run much, much hotter.
So if your site survey didn't account for that heat load.
You're in big trouble.
Yeah.
You'll create hot spots, you'll risk equipment failure. It all goes back to the planning.
A perfect example. Okay, let's switch gears from super high-speed fiber to the workhorse of the rack. Good old copper.
Right. Ubiquitous for those shorter 10-gig links.
So the question is, which specific cable standard lets you reliably run 10G base APT over the full 100-meter distance?
That requires Cat6a. The A is for augmented.
A lot of people might just reach for Cat6. What makes that a case so important? Why is it mandatory?
It all comes down to physics, really. Crosstalk and signal loss over distance.
Interference from other tables.
Yeah, what we call alien crosstalk. At the high frequencies needed for 10 gig, that becomes a huge problem. The Cat6 spec demands much better shielding and tighter twists to fight that interference.
And if you choose wrong,
You fail the planning phase, you end up with dropped packets, intermittent connections, things no professional can afford.
fascinating. So that brings us to section 3. We've got the architecture, we've got the cabling. Now we need protocols to guarantee reliability.
Exactly, planning for things to go wrong. And let's start with the most sensitive traffic storage.
Right, things like FCOE or ISESI. You cannot lose a single packet there.
It's catastrophic if you do. So what's the protocol suite that gives us that lossless transmission guarantee on Ethernet?
The technology required is data center bridging, or DCB.
Right, and DCB isn't just one thing. It's a whole suite of enhancements. But the absolute core mechanism is something called priority flow control, PFC.
So standard Ethernet, when it gets congested, it just starts dropping packets.
It does. PFC is different. It sends a pause frame back upstream. It basically tells the sender, hey, slow down for a second, I'm backed up.
So it prevents the packet drop from ever happening.
It does. And it's smart enough to only pause the sensitive storage traffic, not everything else. It's a key part of planning a reliable data center.
Okay, so DCB handles data integrity. What about network availability? You have to plan for a router to just die.
It happens.
So how do the servers and other devices stay online? What are the two big protocols for default gateway redundancy?
This is a classic. It's handled by the two major first-hop redundancy protocols, VRRP and HSRP.
Virtual router redundancy protocol and hot standby router protocol.
That's them.
Functionally, they do pretty much the same thing, right? They share a virtual IP address that can float between routers.
They do.
Yeah.
But from a planning perspective, there is a very important difference between them.
And what's that?
Vendor support. HSRP is historically a Cisco proprietary protocol. It's everywhere, but it started with them. VRRP, on the other hand, is the open IETF standard.
So the choice you make in the planning phase could determine your level of vendor lock-in down the road.
Exactly. Knowing both is critical because they solve the same problem, but they answer different strategic questions about your vendor ecosystem.
That really adds some strategic weight to the answer. Okay, this focus on resilience brings us right back to that massive 51% chunk. Section 4, the hands-on realities of deployment.
This is where the planning really hits the pavement, the messy stuff people forget.
The facility layer.
Yep. So you're doing a site survey, you're getting ready to install all this expensive gear. What are the two absolute must-check environmental factors?
Our sources are crystal clear on this. Number 1, available cooling capacity and airflow direction. Number 2, power availability and the socket types in the racks.
And these are non-negotiables. Why? Because if you get them wrong, fixing them later is a logistical and financial nightmare.
Let's take power. You order a bunch of switches that need 3-phase power.
And the racks only have single-phase outlets. Now you're talking about bringing in electricians, expensive facility changes, massive delays.
And cooling is even more subtle, isn't it?
It is. You might have enough total cooling for the room, but if your gear is fighting the airflow, sucking in hot air from another rack's exhaust, you create these little pockets of heat.
And that just cooks the components over time.
It kills them. It reduces the lifespan of your expensive ASICs and optics. It's the difference between a smooth deployment and a 6-month delay waiting on an HVAC contractor. That's why it's 51% of the job.
It makes total sense. Now, let's plan for the worst-case operational scenario.
Okay.
The network's up, but something's gone horribly wrong. A bad config, maybe. Your remote management network is totally down. No SSH, no WebGUI. How do you get in and fix it?
You fall back to the oldest, most reliable tool in the box, the serial console port.
In this day and age of automation and orchestration, is the physical console port really still that important? It feels like a legacy thing.
It is absolutely 100% essential. It is the ultimate out-of-band management method.
Because it doesn't rely on the network at all.
Zero IP configuration.
Yeah.
Zero network connectivity. If you've created a layer 2 loop that's brought down your management interfaces, or you've just fat-fingered an IP address, the console port is your only way back in. It is the break glass in case of emergency for every network engineer.
That's a great way to put it. Okay, last point on readiness. We've planned for redundancy with dual power supplies. How do we actually prove that it works before we go live?
Through failover testing.
Simple name, but a critical step.
It's crucial. And it's not just, yanking a power cord out of the wall.
Right.
It's a controlled test. You simulate the loss of the primary power source while the switch is actually passing traffic under load. The goal is to prove that it seamlessly fails over to the secondary PSU with zero interruption to the data flow. It's how you validate your physical high availability plan.
That whole section just hammers home the importance of operational readiness. Okay, let's look to the future. Section 5, modern network operating systems.
We're definitely seeing a shift away from traditional closed proprietary systems.
Toward more open, flexible solutions, especially for cloud-scale data centers. So which Dell Networking OS is built on open source Linux for exactly that environment?
That would be the enterprise SONiC distribution. SONiC stands for Software for Open Networking in the Cloud.
And SONiC is a real game changer, isn't it? How does it impact that 51% planning phase?
In a huge way.
Yeah.
Because it's built on Linux, you get all these amazing benefits. It's modular, so you can update components individually. It's vendor neutral.
Which means you aren't locked into one hardware provider.
Exactly. And most critically, it's incredibly programmable using standard Linux tools and APIs.
So how does that practically change the job of an architect planning a huge deployment?
It shifts the focus. It moves away from just knowing one vendor's specific command line interface and moves towards software integration skills. You can pick the best hardware for the job, regardless of brand, and run SONiC as the consistent OS layer on top of everything.
That reduces risk, supply chain risk, cost risk.
It's a massive strategic advantage to have during that planning stage.
Thank you for diving deep with us.
Until next time.